Today we look at something called the slope of the tangent line, and we are going to look at the slope of the tangent line at a specific point today. And that point that we're going to talk about is point P. Point P has an x coordinate that we're going to call it x, and a y coordinate. We're not going to use the term y. We're going to call it the function's value at x, which is f of x. And to the x value, we're going to add a distance of h, and we're going to call that point Q. So if we add h to our x value, the new x value is x plus h, and the new y value is the function's value at x plus h. So what that means for us is our change in x is the value of h, and our change in the y value is the top y value subtract the bottom y value. And remembering now that slope is simply your change in y over change in x. Right now, the tangent line that I've drawn at P looks good. It looks like it might be touching at one spot, maybe not. But if I grab that thing and I move it just a little bit, how about now? Does it look better or worse? Or what happens if I move that down and move that up just a little bit? Which one's the right tangent line? Today we're going to try and figure out which one is. So I'm going to use my best estimate here as kind of a guide. And here's the basic logic. What happens if Q gets closer to P? What if we put Q right there? And we go to here. And now our value of H is there. Would you say that the line PQ is getting to be closer to the tangent line that is drawn, or will have the same slope? And the answer is yes. Well, then what happens if Q gets moved to here? And the distance between x and h becomes even smaller. And what if it gets closer and closer and closer? In fact, so close that the points are infinitely close together. Or in other words, the h value, the difference between p and q and the x values, is becoming very, very small. Then the distance between p and q becomes very, very close. Well, we would say then that has to be very, very close to the slope of the tangent line. And we talk about that limit as being derived as being the derivative. And when we talk about it, we're not always going to say that this is the derivative with respect to x, which is what we're going to be doing, but we are going to use some other notation. The first one here is the dy over dx. And the way you say that, at least the way I say it, is simply dy dx. And that refers to the slope of the tangent line at a point. This one is f prime x, and that also means the derivative, and you can also have y prime, which means the same thing. And so it's just a short form to say the derivative. And the derivative is the slope of the tangent line at any point for a function. So let's look at an example. This is a parabola, as you well know, that opens down. We are going to find dy dx, which is the slope of the tangent line at any point. And for us to do that, at least at this point, we need to then find the limit as the 2 points get really, really close together, p and q. As the h value approaches 0 of the function's value at x plus h minus the function's value at x over h. Now, just want to remind you where that came from, that is simply your slope. The rate of change of y, which we said is f of x plus h minus f of x, over change in x, which is h. That's all we're doing, is we're looking at the slope. And we have done these already. And we should know that when we find this limit, we end up replacing x with x plus h. Look at that, I already forgot my limit expression in there. There should be limit as h approaches 0. And then we simplify. Now the place you'll make a mistake is you'll do this. You'll go, well, x times x is x squared. You get 2x h's and h squared. But you'll forget that this minus sign right here affects everything within the bracket, so that you have two choices. Some people like to put brackets here. That's not the way I do it. I switch the signs when I write them down. So instead of having those brackets there, I would get rid of the brackets and then simply put the minus there and divide by h. Now what happens is every time you do this correctly, that all the terms without h should be gone. I made a mistake here, guys, when I wrote this down right here. That should have been bracket around the x plus h. Oh no, I did it right, didn't I? This should be a minus. Oh, where am I making my mistake? No, I'm good. I'm good. I just forgot to do the f of x here. Sorry about that. Give me a second here. So 4 times x plus h is 4x plus 4h. That's fine. I forgot to subtract my f of x. The reason I knew that is because all the terms without h should be canceling out. So this right here is my f of x, which is right here. And this is my f of x plus h. And as I just said, every term that doesn't have h should cancel out. So for instance, 5 will cancel with minus 5, and negative 4x will cancel with 4x, and negative x squared with x squared. And then what we're left with is something that we can take h out as a common factor. And when we do that, we get 4 minus 2x minus h. And the h's cancel out, and we then again replace h with 0, and we get 4 minus 2x. So that represents the slope of the tangent line at any point. Then to find the slope of your tangent line, that means finding the derivative's value. You'll notice I use f prime. That's the derivative's value at 4, or the slope of the tangent line at 4. So we replace x with 4, and we get our answer. And then to do the opposite, where is the slope of the tangent line equal to minus 6? Well, that is the derivative. It's saying the derivative is minus 6. The slope of the tangent line is minus 6. So we make it equal to 4 minus 2x. And then solve for x. Now we need to do more examples clearly together to get this mastered. And we'll do a couple at the beginning of the class to go through it. That's basic introduction, and hopefully you get the gist of it, and we can sort out the details of